So now on to STEMIs and NSTEMIs. A STEMI is an ST elevation myocardial infarction. And you usually see these when you have a total occlusion of an artery. And they, on an ECG tracing, look like this. So your P wave, QRS. QRS ends a little bit higher. And you have your T wave. And then it returns back to the baseline. Whereas in an NSTEMI, you have your QRS, but then you have ST depression, and then your normal T wave. Okay? And in this video, well, not this particular video, this video is going to be explaining how a normal ST segment forms. The next two videos will be explaining how first an NSTEMI forms, and then a STEMI. Now, little disclaimer, although we're talking about myocardial infarctions, when you see changes to an ST segment, it's because of ischemia and ischemic tissue, not because of infarcts. Infarcts are, by definition, dead, and as a result, they don't have any metabolic activity and they can't change the electrophysiology of themselves. They're just dead scar tissue, whereas ischemic tissue is still alive, it just has a reduced oxygen supply. So even though we're talking about myocardial infarctions, we're actually looking at myocardial ischemia. Okay, so ST segments, what are they? Well, if we have a normal ECG here, we have our P wave, our Q, R, S, and our T wave. The ST segment is between the end of the S of the QRS complex and the start of the T wave. That's this bit here. Okay? And you'll notice that it's sort of, it is a straight line. That's because it's at the baseline, which in normal healthy tissue is 0 millivolts. Okay? So you can see that faint yellow line there. Okay? So the ST segment is usually at 0 millivolts. Now you'll notice that there are two other parts of the ECG that are also at 0 millivolts. We have it here at the PR interval, which is the space in between the P and the start of the QRS complex, the end of the P wave and the start of the QRS complex. And after the T wave here, this bit is called the TP segment, and that's where the space in between the end of the T wave and the start of the next P wave. That's the space in between those 2 points. And all these points are at 0 millivolts. And why is that? Well, the ECG tracing is simply a measure of changes in voltage. So with the P wave we have an increase in voltage because we have depolarization firstly, and that depolarization moves towards the overlying lead usually. Okay, so we get an increase in the voltage measured. So we have a positive voltage measurement there. With the QRS complex, it's the ventricles depolarizing, hence why we get the QRS complex. We have depolarization moving towards and away from the lead, depending on where it is. And the T wave is the repolarization, which is repolarization moving away from the overlying lead, hence why it's positive. Okay, if you watch the previous video, I explain all of that. Now, the reason these are all at 0 is because at these points, at the PR, at the ST, and at the TP segment, at all these points, the lead is measuring the heart in a state of unchanging charge. Okay, so the ST segment is the ventricle. So if we draw a diagram of the ventricle, I'll try and draw it in line with all these. I'm going to move this out of the way. Okay, so at this point here, if we draw a little ventricle with an overlying lead, we have depolarization moving from the atria towards the overlying lead. With a PR interval, the ventricle is still at rest, okay, because there's no signal travelling through it at this point. With a QRS complex, by the end of it, the whole thing is depolarized, but during it, we see a wave of depolarization moving through it, okay? So that's first going to move down here, and then up the ventricle. In the ST segment, in the ST segment, the whole ventricle is depolarized. And in the T wave, that depolarization is now moving, that repolarization I should say, is now moving away because there's repolarization now moving this direction. And at the TP interval, the heart is back to how it was over here. So, what does that mean? Well, at all these points where we have 0 millivolts being read, we'll notice that there is no movement of ions at any of these points, and because there's no movement of ions, there is no change in voltage. Now, because there's no change in voltage, that means that there's 0 millivolts being read, and that is why at all these points the ST segment is at 0 millivolts, okay, including the ST segment. So in normal healthy tissue, the ST segment is at 0 millivolts. Okay, so hopefully that'll make sense. If you have any questions, leave them in the comments below, and I'll get back to them. In the next video, we'll be explaining NSTEMIs.